All right, so good morning, everyone, and sorry about the slight delay. Interesting things to talk about. Sure. Yeah, happy to present to you Jose Antonio Marin Guzman, who's been working with Nicole Younger-Halpern, who most of us know, at the University of Maryland, and has some fascinating new proposals about what they call bottom-up honest gates. So without further ado, I'll let Jose Antonio tell you what it's up to.
Well, thank you very much for the introduction, and thank you very much for being here, having me here. Yeah, I'm going to talk about this implementation proposals for quantum autonomous gates. What I'm presenting is based mostly on this preprint here, but our sort of like philosophy behind thinking about autonomous machines is more fleshed out in this paper that got marketed as a review, but I don't like to think of it as a review. Anyway. Okay, so autonomous quantum machines, these are basically devices that perform tasks, and the quantum Hamiltonian that is responsible for the execution of this task remains constant throughout the protocol. So basically what this means is that we're interested in protocols that there's no interference through classical time-dependent control while the protocol is being carried out. So examples of this can be refrigerators where you have a system and you want to deplete excitations in it, engines in which you want to pump excitations into a target system, and autonomous quantum clocks that I'm going to be discussing more at length a little bit later, which is sort of like a clever engineering of a quantum heat engine. And sort of the motivation behind thinking about autonomous quantum machines, we have two of them, which is classical control in quantum information processing platforms can limit some of the capabilities of this. For example, if you think of superconducting qubit platforms, you are fitting wires into a chip, which fundamentally limits the amount of chips that you can have in your, the amount of qubits that you can have in your chip. And these wires are hot classical macroscopic objects that heat the qubits up and decohere them. So there's this motivation, and also there's a motivation of making quantum thermodynamics more useful. There was a like applying this transformation and energy framework to quantum context has been like fruitful in terms of getting fundamental insights, but when it comes to actually informing quantum technologies, quantum dynamics has sort of like a depth, especially compared with classical thermodynamics and how influential it was for developed technologies. So the state of play of autonomous quantum machines today, we have experiments with autonomous machine in information platforms such as trapped ions and superconducting qubits. These are two kind of recent refrigeration experiments. And there's also this kind of older, but in the same like philosophy of dissipative approach to computation. So in this Sirac paper, which is like the earliest that I know, the idea is that you perform computations by setting up your system and coupling it with a tailored environment. It evolves to a steady state, and this steady state encodes a logical operation or a computation. And there's also this other interest, particularly in the quantum error correction community, in which instead of having some unitary that makes mistakes, you look at them by measuring syndromes and then correct them. You just passively let something evolve, which itself error corrects. So sort of like more orienting towards our actual work, there's this abstract approach for autonomous computation proposed by Markus Huber's group in Vienna, in which you have this sort of like punch card style of computation in which you feed a quantum processing unit some state that encodes a program that means what operation you want to perform and what's the sequence of gates that you want to implement. This is an abstract approach, but the idea is, okay, in this gate sequence that a quantum processing unit could take, how could we, in current technological platforms, implement these logical operations, these gates, in current platforms with reduced degrees of classical control. So in this work, I'm going to be talking about the implementation of autonomous quantum gates in 3 platforms, namely superconducting qubits, trapped ions, and Rydberg atoms. And by autonomous quantum gates, I mean a protocol executed by an autonomous quantum machine that executes a gate. We're interested in single gate realizations in which there's no intervention with the device in the middle of this gate protocol. So as an outline for the talk, again, I'm going to be talking about these 3 platforms. I'm going to very briefly be introducing each platform, but not to a high extent or anything. I'm going to explain well-established gate protocols in this platform. I'm going to be explaining 1 gate protocol per proposal, but there's more proposals in our paper. And then talking about how to perform these protocols autonomously. And at the end, I'm going to give an outlook about what this could actually be interesting for in the future. Okay, so superconducting qubit platforms, we have 2 main characters in cavity QED. First, we have qubits. So introductory E&M, you have a circuit with a capacitive element, an inductive element. Charge is going to oscillate over time. But if you substitute this inductive element with a superconducting element, then you gain an anharmonic spectrum, which means that your successive energy levels actually are mismatched, which is good for information processing in the sense that if you are able to address a single transition, you isolate a single qubit in a completely harmonic spectrum, talking to one transition, talks to all of the transitions. So this is practical for information processing. And the other protagonist in cavity QED are cavities. You enclose light, the electromagnetic field discretizes into independent harmonic oscillators. And sort of in the interplay and the interactions between these modes, these cavity modes, and the transmit qubits, you can process information. So I'm going to give a background for a Z-gate in cavity QED. So this is based, or the protocol that I'm going to describe was from Andreas Waldorf's group. And the setup is that we have a transmon that is coupled to a cavity that has a single mode. The transmon has energy levels G, E, and F. And these are coupled via Jaynes-Cummings interaction. So this Hamiltonian, we just have the free part for the cavity mode, the free part for the EF levels here. And we have an interaction term that exchanges excitations in the cavity with excitations in the EF levels. So the GE and EF energy gaps are mismatched by this anharmonicity alpha. And the EF transition is going to be resonant with the cavity mode. So the gate is executed by shooting a photon into the system, and this photon is going to be resonant with both the EF transition and the cavity mode. So what happens next depends on the state of the transmon. So if the transmon begins in its ground state, the photon is going to come through, interact with the cavity, and get reflected with the pi phase. But on the other hand, if the transmon is in its E state, then the cavity mode and the transmon are going to hybridize. There's going to be an energy split, and this photon, which is resonant with both this transition and this cavity mode, now has the wrong energy to interact with either of them because of the energy split, and it's going to get reflected without a phase. So what does this protocol actually do? Well, if you begin in a superposition of the photon field begins in a superposition of a flux state and the vacuum, then while the transmon is in its ground state, this is going to flip the flux state part of the photon field. And if you're in E, nothing happens. But we are shooting a photon into the system, so we take this photon field to be always in 1. So in a superposition, if the transmon state is in a superposition of the G and E levels, then this up to a global phase executes a minus Z gate on the transmon qubit encoded in states G and E. So again, this is just like a description of this sort of old protocol from Waldorf's group. Now I'm going to describe how to think about autonomy here. So this Z gate is initiated by a photon being shot into the system. And we need to think about some way of autonomously shooting this photon into the system, an autonomous photon source. So we're going to think of photon emissions as ticks from an autonomous quantum clock. this is sort of like a hot topic sometimes. When I say autonomous quantum clock, I mean like a theoretical thermodynamic model that I'm going to explain later. I'm not talking about like ultra precise atomic clocks. This is like a different theoretical model. So the idea is that this autonomous quantum clock is going to provide the ticks that are photon emission events that are going to activate this Z gate. So again, a basic model of an autonomous quantum clock is simply like a theoretical thermodynamic sort of setup in which Markus Hoover's group in Vienna started thinking about what's like the most bare bones way in which you can think of a ticking mechanism. And they came up with this quantum heat engine approach. So in this very simple heat engine that I'm going to describe, we have 3 qubits. These 3 qubits have energy gaps omega c, omega h, and omega t. And the idea is that this heat engine is going to pump excitations into this target system. And once excitations are pumped into the target system, the target system is coupled to an external field so that this pumped excitations rapidly get emitted into the environment, and you can count them as ticking events. So these 3 energy gaps fulfill this resonance condition in which the energy of the middle qubit matches the sum of the energies of the target and the leftmost qubit. And this resonance condition is going to like isolate 2 degenerate states, 0, 1, 0, in which excitations are concentrated in the middle qubit, and 1, 0, 0, 1, in which excitations are on the other 2 qubits instead. So as we want to pump this target system through our engine, we really want to, in some sort of way, induce this transition and hinder the rabbit flop back to 0, 1, 0, as we want excitations to concentrate in the target system. So in order to do this, thermodynamically, you can think about this as, or you can think about a way to do this by setting up heat baths. So imagine that you connect your leftmost qubit to a cold bath at a temperature Tc, and your middle qubit, your hot qubit, to a bath at a temperature Th. So you let them thermalize, and this is going to bias excitations away from the cold qubit and into the hot qubit. And as excitations get pumped into both the target and cold qubits, the idea is that the cold qubit rapidly dissipates. It dumps excitations very quickly into its respective heat bath when compared to like the internal timescale of the rabbit flopping in the 3 qubit system. And that's going to bias the system towards an excited state in the target system. As you get rid of this excitation in the cold qubit, then this flopping back is hindered, and you accumulate excitations in the target system. So one objection that you could raise is that this is a very stochastic thing that I'm describing, but the ticking mechanism and the timing of this can be improved by increasing the complexity or changing the geometry of your two-body arrangement. So sort of like another important thing here that I'm not talking about yet is the fact that we're assuming that these 2 qubits are in contact with heat baths. Heat baths are, very large systems, or at least they're modeled this way. So this thermalization, this rethermalization, even when excitations are dumped quickly into the cold bath, is going to keep happening, and the pumping is going to continue, which is something that you should need to worry about, because if you're continuously exciting this target system, and this target system is continuously emitting, then your gate is continuously being executed. So you require some additional engineering to stop the clocks ticking. And we think about this by substituting the target system, instead of modeling as a qubit, by modeling it as a lambda system. So this is going to have 3 states: a ground state, an excited state, and an intermediate energy, long-lived metastable state, S. So the system is going to be pumped into its excited state via the action of the heat baths. and then it's going to decay into this metastable long-lived state S, and it's going to emit a photon, which is an autonomous quantum clock's tick. And the idea here is that if this metastable state's lifetime is very long compared to the time that it takes for the gate to be executed, then this is enough of a mechanism to stop the ticking. Population is going to concentrate in this long-lived state. It's not going to decay back into zero, and it's not going to be pumped back into one, and it's not going to emit excitations, at least in timescales that are, or at least that process that I described happens in timescales that are longer compared to the execution of the gate time. And in practical settings, the timescale for the Z gate in this Wolfram experiment is upper bounded by a few hundred nanoseconds, and the lifetime of a metastable state in a lambda system engineered from Transman qubits can be of a few microseconds. So, sort of as a recap of this autonomous itinerant photon Z gate, we have a quantum clock that is built from an autonomous quantum heat engine. This quantum clock emits ticks, which are photon emission events, and this photon executes a Z gate encoded on the Transman qubits low energy state. Yes.
I'm a little confused because if I understood correctly, the photon is emitted randomly depending on the branching ratio of this lambda transition, or you're assuming it's emitted every time you end up in set of state?
Like theoretically, we are assuming that this is engineered in such a way that once excitations reach the excited state, they rapidly get emitted. And you can, and this is done.
So you just have a much faster decay second transition.
Yeah. Yes. So really, you're just like interested when modeling this autonomous quantum clock in what the temporal profile of this population is.
But still, it's the talking about it as a clock that confuses me. I don't expect the ticks to be regular. I expect them to be quasi-random. In what sense?
They are stochastic. And in this particular setup where we just have three qubits interacting, it's a bad clock, but you can improve it by adding more qubits and like making a different energy ladder or changing the geometry of your arrangement. That
would actually make the ticks regular.
Yes.
Interesting. Okay. Thanks.
Yeah. There's a there's a, I mean, Marcus Huber's group has worked on this quite extensively, and there's a, I mean, I find it very interesting that it's a paper that talks about how you can get like ultra precise clocks without dissipating a diverging amount of entropy. But yeah, this model, I agree with you. It's a stochastic kind of bad ticking model, but it can be improved. Yeah. Okay. So even though I'm not talking about this today, we also have a dispersive Z gate and an entangling XY gate proposal in our paper. Are there any questions? Any other questions with this superconducting qubit gate? Yes.
So the signal that you were looking at from the reflection from the cavity was the phase shift on a boat.
Yeah.
Right? But if it's emitted spontaneously, then isn't its initial phase random?
I see your point, and that's something that is not detailed in our paper, but I mean, you could have some sort of like passive, like intermediate steps here.
On the photon, or I thought as long as you have one photon,
yeah,
you drove a phase shift on the qubit.
Yeah.
And the photon
Yeah.
expected.
Yeah, that is.
So in that sense, I think the phase of the photon cancels out for that particular.
Yeah, that is true.
It would be different if you made 0 + 1, but I want to measure.
Yeah, you always have like this on a clean clock state. Yeah, you're right. It's this which is superposed, not the photon state. Yeah, that's correct. Okay, so moving on to trapped ions. So in trapped ion platforms, one encodes qubits in the internal electronic states of ions, and being charged particles, you can trap ions with oscillating electromagnetic fields, and this the way in which you trap them, like the geometry of your trap and everything, determines some sort of ion structure that has naturally arising phonon modes. So these phonon modes can be resonant with the internal ion qubit transitions and can transfer information between ions, which is convenient for information processing, since you can have all-to-all connectivity, and also ion qubits are very long-lived. I'm going to be discussing a single gate scheme that could work for either Z gates or entangling Mollner-Sorensen gates. So Z gates on trapped ions, you basically hit an ion with a laser that is detuned from the transition. That's going to make the Bloch vector of the ion qubit rotate. And if you drive this transition for a few microseconds, you can get rotations. These numbers are for calcium ions. And Mollner-Sorensen gates, you want to, at least in our proposal, we're talking about entangling two ions, but you can have like different structures. Actually, the first experiment in Mollner-Sorensen gates, I think they entangled 4 ions. And the idea is that you sort of subject this ion pair to a bichromatic laser field. You have 2 different frequencies that are detuned from the motional sidebands, and these drive transitions between internal electronic states of your ions. So over phase space, this sort of like returns to the same point, but acquiring a geometric phase. And since they're just using this motional excitations transiently, you don't need to cool your ions very much. It's sort of like blind to the amount of phonons that you have in your chain. And you can reach entangled states by shining on your ion sets for a few tenths of microseconds. Again, this is for calcium ions. So in our proposal, we suggest using a tailored potential slide. So the idea is that you trap your ions with in a way that has some sort of like spatial gradient in, say, like an axial direction. And I'm saying this very easily, but this is kind of it requires like an intricate enough electrode structure in your trap. And you turn off part of the potential, namely like the axial or the part that has this spatial gradient. But you need to keep some trapping, because if not, you'll lose your ions. But you switch off part of the potential, and the ions are going to slide through this landscape. So the idea is that you have some zones that are pre-illuminated by laser beams, and as the ions pass through these zones, they undergo gates. So we're substituting like the action of turning on and off a pulse by instead making the ions move through these illuminated zones. So in order to affect the gates, we propose using flash lamp lasers that are charged before the gate execution. So this enables quantum autonomous control. So the idea is that you don't really want a pumping mechanism in your gain medium, re-exciting the population inversion, but rather having a single charge and having it emit a single pulse. So a single pulse can last for tens of microseconds, which is an appropriate duration for C gates and possibly Mollner-Sorensen gates without the need of repumping. And these lasers can also be appropriate in terms of wavelengths for both realizations. So as the recap for the gate proposal, you turn off part of the potential that you have, the ions are going to slide through, and we're replacing this pulse action by having gate zones that are illuminated throughout the protocol of the ions passing. It's important to notice that the ions, like the interval in which they're exposed to the light, depends on like your initial trapping, so that depends on how your electrode structure is set up. And this slide proposal is different from shuttling protocols that have been performed lately, in which you move the potential. In this case, we're not moving the potential, but we're rather turning it off partially. And we're proposing this laser field to be provided by flash lamp lasers. Yes.
issue in general the two atoms to have different velocity after eternal sign? Because I imagine like this picture, the left atom is the accelerated one. Is this an issue?
I would say that more than that, some of the issues that you could have with this proposal come with entangling gates, since you're not holding them here anymore, they're going to naturally repulse a little bit as they traverse through, and that's going to destabilize the radial modes that you would use to entangle the ions. But I don't think that velocity is that much of an issue as like the mode destabilization. Yes.
Would it not be possible for significant gates? This
Like entangling gates are trickier, or potentially could be trickier because of, again, the modes destabilizing. We didn't rigorously like do calculations of this. But yeah, entangling gates could be difficult to perform. Single qubit gates, they should work. Entangling gates, the mode destabilization definitely plays a part.
Like, can you do entangling gate for arbitrarily, like two arbitrarily cut ion, or you can only do it?
You can do entangling gates for, so sort of like I'm not gonna go back, but like the one of the powerful ideas of information processing with trapped ions is that you can have these structures in which modes are like collective modes of the whole ion thing. So the whole ion chain shares this these phonon modes. So if they're resonant with like the right qubit transitions, you can use this to entangle any two or more ions in the chain. Yeah. But we're not considering this in this proposal. That's just like a general. Yeah. Okay. Oh, yeah. Also on our paper, we I forgot about this one. We discussed a ring trap gate, which conceptually is kind of the same thing, but instead of having a slide, you consider like an ion structure in which ions are revolving around each other. But that's detailed in our paper. I'm not going to talk about this. Okay, so the final platform that I'm going to be talking is Rydberg atoms. So Rydberg atoms are just neutral atoms in highly excited electronic states. And these highly excited electronic states sort of like give these neutral atoms very exaggerated properties, very large sizes, very large electric dipole moments. And you can leverage these strong interactions for creating entanglement. So, I mean, the amount of control that has been achieved with Rydberg atoms with recent experiments is overwhelming. And some really coveted like information protocols, such as distilling magic states or having fault tolerant gates, have been performed. And also they have like the highest fidelity gates performed with any platform. But I'm going to be talking about ultra-fast interactions in Rydberg atoms. So the entangling protocol in a Rydberg atom platform usually relies on Rydberg blockades. So the idea is that you have two nearby atoms, you excite one of them to this highly excited electronic state, and then the action of this atom is going to affect the energy levels of the nearby atom. So when you try to address it, or when you try to address its Rydberg transition, because of the shift of levels, you're basically not talking to the Rydberg transition anymore, and you effectively blockaded it. So these Rydberg blockades typically occur in like half a microsecond, but this is not really a fundamental speed of Rydberg platforms, but rather how long it takes to induce this Rydberg transition and how long it takes for the shift to occur. If you have two atoms interacting via dipole-dipole interaction, this coupling is actually in a gigahertz scale, and thus like the speed limit for entangling highly excited atoms is in the order of nanoseconds.
That's assuming what distance between the atoms, 3 gigahertz?
So this idea is taken from this from Kenji Omori's lab. In their platform, they use tweezers to like modify this distance, but it's around a few micrometers. I may be wrong, but I think it's like around 3 to 4 micrometers. Okay, I could be wrong. Okay, so the idea is that the idea from Kenji Omori's lab is that you can excite two atoms simultaneously to the Rydberg states by using laser pulses that are short enough and powerful enough so that they're both excited to the Rydberg states before the blockade has any time to happen, and you can effectively have like atom pairs in Rydberg states. So the protocol for this ultra-fast excitation is that you, again, excite both atoms to the Rydberg states via laser pulses that last for picoseconds. These are two photon processes. And once these two atoms are excited to the Rydberg state, you just let them interact for a while. So in Omori's experiment, this DD state is reached upon this simultaneous Rydberg excitation, and it's degenerate with this entangled PF state. So this Rabi flop of DD and the PF states, if you let it evolve for long enough, is going to leave you in entangled states. So you let these two atoms interact for a while, they entangle, and you can bring them back to your computational basis, but now they're entangled. So thinking about like inducing this ultra-fast excitations and interactions with quantum autonomous control sort of like obligates you to think about a source that is autonomous for these short pulses that could be a passively mode-locked laser. So this type of laser needs no external control to pulse, since they have an absorbing element inside that discriminates waves according to their intensity, and they build up to these very, very short picosecond length pulses. And again, as in the trapped ion proposal, this control is going to be autonomous as long as there is no repumping in your laser system. So these mode-locked lasers can also are also like wavelength appropriate for the two photon processes driving this Rydberg transition. But we also need to think about successive pulses, since we excite, let them entangle, and de-excite. So since we don't have like any central timekeeping unit telling a laser pulse that enough time has passed, we propose using an auxiliary laser to time the pulses. So the idea is really not too complicated. It's actually kind of very simple. You just have a laser that you want to emit at a time 0, a laser that you want to emit at time t, and you just place an auxiliary laser long enough from your second laser and activate the first laser and the auxiliary laser together. So the first laser does its magic while the other laser pulse is traveling. And after an appropriate time, the second laser emits. So aside from being short, these ultra-fast excitations need to be very powerful. So in order to amplify the power of these pulses, we propose using an enhancement cavity. So the idea is that you enclose your Rydberg atoms in a cavity whose length is so that the round trip of a pulse matches the pulse's repetition rate. This is going to make the pulse intensity build up inside the cavity. But in order for this to work, you would need these two atoms to be so the idea is that you begin in these atoms in a state that is different from the one that creates a Rydberg transition, because you don't really want this weak pulse to be hitting your atoms and during your transition. So you set them up in another state, and then via an auxiliary pulse, you bring them to your transition that is now correct after the pulse has built up, and that pulse is going to bring them to the to the Rydberg states. You look like you have objections. Okay, so this ultra-fast entangling gate protocol, we propose exciting two atoms to the Rydberg states and letting them entangle via their dipole-dipole interaction. So the ultra short pulses and the timing are provided by these passively mode locked lasers, and you can enhance these the power of these pulses via an enhancement cavity. Are there any questions with this? Yes.
Sorry, maybe I just got lost. But what makes these autonomous?
So the autonomy part comes from the fact that you need a way to emit this ultra short pulses with a laser that you're not actively operating, and this happens with these passively mode locked lasers because of their satural absorber. So in order to time several pulses, we propose using auxiliary lasers, and it's autonomous in the sense that you're not actively driving these photon sources. Yeah. Yeah. Okay. So again, I just talked about 3 different gate proposals in 3 different platforms. One was a Z-gate in superconducting qubits. The other one was a tailored slide proposal for trapped ions, and this ultra-fast interaction gate in Rydberg atoms. So what venues does this actually open for future work? Well, first, actual experimental implementations of these proposals, which should begin with proof of principle autonomous quantum gates, and then trying to see how these could actually be incorporated into quantum devices. Also, in the spirit of the quantum processing unit motivation that I gave at the beginning of the talk, it's also relevant to think about autonomous ways to concatenate gates and this was a point of contention that I didn't expect in the review process. We're proposing single gate realizations, but we're not actually proposing full-fledged autonomous quantum circuits. And that's definitely an expansion that could be worth thinking about, like either in these proposals or in other autonomous gate proposals, like, is there some sort of way that when one gate happens, some other system is activated autonomously and you can build up sequences with that? And then this is something that we were talking about, autonomous implementation of other steps. Again, we're talking about single gate realizations, just looking at the very short time frame in your quantum computer where you're executing a single gate, but initializing your states, quantum error correcting, is something that we're not thinking about in this work, and it could be a direction for future work, especially in quantum error correction. So again, as I was mentioning in the beginning, there's this interest in the error correction community to not have to measure syndromes, or what alternatives are there to syndrome measurements and correcting unitaries, which should fit in some way with our autonomy philosophy, but that's definitely for future work. And also, before thanking you, I mean, I'm here today, I'm visiting, and aside from this, I also like to think about many-body physics. So I've been especially thinking about sort of like magic in this kind of like setups in which you have noise in the middle of it, and also about symmetric, monitored, random dynamics. But I'm also interested in more many-body physics that I've read about, but never had like good enough ideas to actually drive a project. But yeah, if you want to chat about this, I have some. We can set something up in the afternoon or an email or something. And yeah, thank you for your attention.
Thank you very much for a great talk and several different physical platforms, which is always nice. We have time for questions.
Yes.
Yeah. Thank you for the talk. I'm curious, like, so you mentioned a lot of autonomous gates on different platform. Have you do theoretical analysis on, like, for example, the gate fidelity and compared to like the current experimental platforms? Like all the platforms are currently experimentally available, and they do have like a pretty good like gate fidelity already. So have you computed like yeah?
So we have, in terms of theoretical calculations, in our paper, we compute some gate fidelities and phase shifts for C-gates in superconducting qubit platforms. And I also mentioned, but very briefly, that we have like an entangling XY gate proposal in the superconducting qubit. Yeah, in the superconducting qubit part of the paper, and that XY gate really requires some more thorough modeling, and that's something that we want to think about in the future with our collaborator, Simone. So yeah, in the other platforms, especially in trapped ions, it's kind of difficult because it's very, like, our proposal is very dependent on like how the electrode structure is actually constructed. So an analysis is more difficult, but yeah, it's something that we're thinking about. Yeah, but not in much detail in this paper. Yeah.
Other questions?
This is a question. When you mentioned you were using flash lamp lasers because you didn't want any kind of external control from the user.
Yeah.
I'm a little bit confused by this because wouldn't you still need some kind of, let's say, external thermal temperature control, for instance, which would have some kind of classical control inputs from the user? And the same way you can think of the thermal baths that you have in your clock example, wouldn't one to ensure that they have a certain they are evolving with this Hamiltonian that you define your definition of your autonomous machines by, to ensure that you have the single Hamiltonian, this would also require external classical control. So I guess I'm confused by why we can have certain forms of, external classical control and not other forms.
So to answer the first question regarding the flash lamp pump lasers, the idea is that you want some laser that is not continuous wave, that you don't have to like be pumping to activate some pulse laser that lasts for long enough to induce these transitions in ions. So the laser systems that we found that could enough.
So in all the cases you're using, you're only relying on a single pulse from the laser, pulse to the right?
Yes.
Okay.
And regarding the heat bath question, I mean, in the clock, we're just connecting these qubits to heat baths, but we're not like.
Well, sorry, I guess it's from a place of ignorance, but I was asking if maybe to ensure that it's the heat bath that you think it is, in practice, you need some form of classical control. Like, for instance, if we're just thinking in terms of temperature or something that's too hot, you need somebody to have to be cooled down, you get a constant temperature.
I mean, I think that the heat bath, like these abstract heat baths that I'm mentioning here, don't really consider like the difficulties of actually having a heat bath.
So I was thinking if then we can have classical control in the heat baths, what's stopping us from just using like a diode laser, a solid state system, and then we can avoid all these sort of nightmares of having gas lasers.
But something that is maybe worth mentioning is that in this kind of thing, like systems where like the heat baths are there to bias some state that then evolves into something. So we're not really interested in that much in like what the actual heat baths look like, but rather we want a gradient that creates some sort of bias.
But I think the question raises an interesting point, which is a lot hinges on how we define autonomy. And we can just take a very abstract definition for the theoretical interest of it. But then in the end, when you say, I imagine that I just have an infinite bath of boiling water, but everyone knows that in reality, you're going to have some servo system locking the temperature and it won't truly be autonomous. you've got to ask, does it make a practical difference? So I'd kind of like to come back to your motivation, where you made the nice point that a real stumbling block, let's say in the superconducting computers, is as they scale them, they need more and more control wires going into the cryostat. They dissipate heat. There's a limit to what you can do practically. If you could reduce the number of control wires you needed, that would be great. I'm not sure if I see the connection between the kind of gates that you're proposing and an actual reduction in, the amount of control that needs to go in and out of the cryostat. Is there anything you can say about really, reducing the amount of external control in that sense and still accomplishing a calculation?
So I would say that this particular gate proposal here really doesn't, like, the classical control that we're reducing is more from like the photon source than the actual.
Right, but
Yeah.
that's my point, is that's interesting conceptually, except
Yeah.
practically, we have no trouble controlling photons, controlling them rapidly, making pulse sequences. We do have trouble getting electrical signals in and out of a cryostat.
Yeah.
So if there's something that one of the superconducting proposals could do on that side, I feel like it would be easier to sway people and convince them this is an important definition of autonomy, not just,
Yeah.
something we wrote down on a piece of paper.
Yeah, but I agree with you in that sense that when we embarked upon this paper, like, sort of like the how to say this, like I found myself making up excuses or caveats for fitting into autonomy rather than sort of, and like straying away from like this guiding question, which is also like it's also a concern that I share. Like this is
Yeah. No, and that's normal. I'm just
difference that, yeah.
asking whether you had thoughts on the next step, or if not, encouraging you that
Yeah.
to move from that abstract point, it's
Yeah.
often powerful to try to connect it to some practical advantage. Can I ask you a more down-to-earth question? Towards the end in the Rydberg scheme, you showed an enhancement cavity, and I wasn't sure if I'd misunderstood something, because I thought all of your control is through femtosecond pulses.
Wait.
But in order to get any enhancement, doesn't your cavity need to be resonant with your photons, meaning that the photons need to be narrow band, meaning that they're not short pulses? Isn't there a conflict between the idea of the enhancement cavity and the ultra-fast operation?
So I'm not sure I understood the cavity being resonant with the.
Well, so what do you mean by an enhancement cavity?
I just mean something that, is able to make like the pulse train, the incoming pulse train, build up on its own. So like the pulse that bounces back and forth, like constructively interferes with the other incoming pulses from the train, and that makes it more powerful. Like that, yeah, that's the idea behind this. But it's,
Okay.
yeah.
So since that requires constructive interference, it does require, some coherence in the cavity. But I guess you're right. If the cavity is designed to be synchronous with the pulse train, then you can make use of the coherence between the different pulses, even without having a narrow band laser itself. Maybe that's possible. Okay, it's really missed. Any other questions? If not, then please join me in thanking Jose Antonio.